For today's lesson, we're going to be looking at the properties, or some of the properties of limits that we've been talking about. So, generically, given two limits, let's say that the limit of my function f of x as x approaches c is L, and the limit of my g function as x approaches c is k. Then 5 of our properties of limits are stated below. The first one is what we call a scalar property, and it says that if I wanted to find the limit as x approaches c of a scalar b times f of x, then that would simply be b times L. And the second one is the sum and difference property. If you were to find the limit as x approaches z of two functions added together, f of x plus g of x, and that would simply just be L plus or minus k. The third one is called the product property, and basically it says if you wanted to find the limit as x approaches c of f of x times g of x, then that value would simply be L times k. 4 is called the quotient property, and if you want to find the limit as x approaches c of f of x over g of x, then that would just simply be L over k, as long as k is not equal to 0, because remember, you can't have defined. And then finally, the power property, number 5, the limit as x approaches c of f of x raised to the nth power would simply be L to the n. Well, if you're anything like me, I like to have a little bit more of a concrete example. So let's say that I told you that the limit as x approaches c of my function is equal to 5, and that the limit as x approaches c of my g function was equal to 3. Let's say that I wanted you to find the limit as x approaches c of 4 times f of x. Well, then that would mean that my answer would simply be 4 times the limit of f of x, which we already know is 5, so the answer to that would be 20. For number 2, let's say I wanted you to find the limit as x approaches c of f of x plus g of x. Well, that would be simply the independent limits added together. So the limit of f of x we said was 5, plus the limit of g of x we said was 3, so 5 plus 3 would give me 8. For the next one, let's say I want to find the limit as x approaches c of f of x times g of x. Again, since we know the limit of f of x is 5 and the limit of g of x is 3, so 5 plus 3 is 15. And those are check marks. I'm going through each one. The fourth one, let's say I ask you the limit as x approaches c of f of x divided by g of x. Well, then that would simply just be 5 over 3. Just a check mark. And then finally, if I wanted you to tell me what the limit as x approaches c of f of x raised to the third power, then that would simply be 5 to the third power, which would be 125. Now, so limits are very wonderful to work with. One of the most convenient analytical ways of evaluating a limit is what we call direct substitution. So you remember we talked about numerically and graphically how do we determine limits. Let's look at a more algebraic or analytical way of evaluating limits, and that's called direct substitution. So let's say I wanted you to tell me what the limit as x approaches 2 of 4x squared plus 3 is. Again, you could graph 4x squared plus 3, but let's say you didn't have a graph. Let's say you didn't have a t-table. One method that we would use to solve this is by direct substitution, which means you literally evaluate the function, the limit for that x value. So you'd have 4 times 2 squared plus 3, so that would be 4 times 4 plus 3, so that would be 16 plus 3, so that would be 19. So that limit is 19. Probably, well, why did you teach this to us to begin with? Well, direct substitution works, and it's valid for all continuous polynomial and rational functions with non-zero denominators, as well as radical functions that don't have imaginary numbers, and all of our trig functions as well. The key point is here, it works whenever you have a continuous function. Now, there is problems with direct substitution. If you do direct substitution and you get indeterminate form, in other words, 0 over 0, then direct substitution fails and you have to do some other method, which I will teach you later on. For now, direct substitution is going to be our go-to method. So again, let's say I ask you to find the limit as x approaches 1 of the function x squared plus x plus 2 over x plus 1. Don't be intimidated, just do direct substitution. So literally evaluate the limit at 1 And again, that kind of sounds like, well, I thought we didn't really care about what the function is at that point. That is true. We don't, with a limit, we don't care about what the function is at that point. But remember what I just said, evaluate the limit at that particular value. And so plugging in 1, you get 1 squared plus 1 plus 2, so that would be 4 over 2, and that gives me a value of 2. You could verify both of these answers graphically or numerically. But again, direct substitution is your go-to method, I would say. Now, let's apply direct substitution to function composition. Remember, we talked about function composition in pre-calculus. Well, let's say that you had a function f of x is equal to x squared plus 4, and let's say you had another function g of x that was equal to the square root of x. What if I wanted you to find the limit as x approaches 0 of g of f of x? Let's do g of f of x. Yes, that's the one I want. Okay. So the limit of g of f of x. So remember, whenever you do function composition, you always start on the inside function and work your way out. So this would be me evaluating f of x function inside of the g of x function. So what would that look like? Would that be the limit as x approaches 0 of a function inside of g function? So that would be the square root of x squared plus 4. So then you can just do direct substitution now, and you would get the square root of 0 squared plus 4. So you get 4, and the square root of 4, that would be 2. So that would be my answer for the problem. Now, another way that you could have done that is simply do direct substitution, plug 0 into x squared plus 4, and you would get 4, and then simply take the square root of that, and the square root of 4 is 2. So again, direct substitution also works on function composition as well. It also works on our trig values, trig functions, as long as you get a real answer. And with that being said, there are two very important trig limits that I'm going to give you right now. So two very important trig limits, and they are as follows. The limit as x approaches 0 of sine of x over x, and we've discussed this in a previous video, that is equal to 1, always and forever. You can verify that numerically or graphically. We won't verify that analytically, but I'm just telling you the limit as x approaches 0 of sine of x over x is equal to 1. And the other one, the limit as x approaches 0 of 1 minus cosine of x over x, that is equal to 0, always and forever. And again, you can verify both of these if you want to graphically, but just know that you need to have those memorized whenever you're taking an assessment. So again, direct substitution is going to be your go-to method, and it works well with all continuous functions as long as you get a real answer for it.